Hi everyone, welcome back to the second part of the lesson on pressure. So let's just dive into it now. So first of all, just like to recap what we have done so far. In the previous lesson, we have already covered the question on why is the pressure of fluid not dependent on the contact area. And the second part is if the pressure of fluid is not dependent on the contact area, then what are the factors that affect its pressure? So in this lesson, we're going to focus on the next two items. The first item is one that a lot of students are very confused about, and that is why the ideas of hydraulic is so different from that of the other pressure questions, especially that of liquid pressure, because they are using very different formulas and very different principles. And the second question is how to understand the idea of atmospheric pressure. Okay, so without further ado, I'm going to start with the first item. So let us just recap on the differences between hydraulic and fluid pressure. Okay, hydraulic is governed by the principle known as the Pascal's principle, where it states that pressure is transmitted equally throughout the liquid. All right. However, for fluid pressure, the pressure is dependent on the depth of the fluid. The deeper, the higher the pressure. And for hydraulic, the pressure formula that is commonly used is F divided by A, while that of fluid pressure is usually H rho G. And for hydraulic, only liquid can be used. You cannot use gas because liquid is the only fluid that is incompressible. Gas is compressible, so it cannot be used as a hydraulic fluid. For fluid pressure, this formula H rho G is applicable to both liquid and gas. The next one is the key factor in hydraulic is the area of the pistons. Alright, while that of the fluid pressure depends on the formula H rho G, so the depth, the density, and the gravitational field strength. So in a nutshell, the difference between hydraulic and fluid pressure can be summarized as their application is very different. Okay, so the main reason is because hydraulic pressure and fluid pressure are asking different things, so they are using different principles to get the solution. For fluid pressure, it is applied when we are trying to find the pressure of the fluid at a certain depth, while for the hydraulic pressure, it is applied when the liquid is completely enclosed, alright, which I will elaborate further later. And a force is exerted at one point, and this force will create an equal pressure throughout. Okay, so next part I will explain this. So let's look at the fluid pressure idea first. So for fluid pressure, okay, let's say we want to find the pressure at points A and B, which is A is 3 meters below the water level, and B is another 2 meters lower than A. All right. So a simple calculation will be using H rho G. In that case, the pressure of A will be 3 times 1000 times 10, which gives you 30,000 Pascal. All right. So very simple. Now for B, of course, we do not use the value of 2 meters, but we have to calculate based on the overall depth of B from the surface. So in this case, it will be 5 times 1000 times 10, or 50,000 Pascal. So the deeper the depth, the higher the pressure. So fluid pressure is very straightforward and very simple. Now what happens if we consider the same container of water, but in the idea of hydraulic? So what is so different about hydraulic, and what does hydraulic ask that requires a different principle? Now for hydraulic pressure, okay, the first thing you realize is that the vessel is completely enclosed. In other words, the water in here has no space to expand into. It cannot go anywhere else. There is no airspace. There's no vacuum inside. There's no way that the water can escape, right? So what happens is that imagine there is a small opening here where a piston is inserted, all right? So what happens if this piston, you apply a force of say Fx, all right? When you apply a force of Fx over an area of a piston of Ax, okay, a pressure is exerted, and this pressure Px is equal to Fx divided by Ax. So what happens is that this pressure Px, okay, is transmitted equally throughout the vessel. So at any point on the vessel, the pressure is Px, regardless of whether it is higher up or at the lowest point. So in other words, if there are other pistons around the vessel, they will also receive the same pressure regardless of its position. Okay, whether your piston is high up or lower down, okay, they will also receive the same pressure. It does not mean that at a deeper depth you will have more pressure than the one above, because in hydraulic question we are only interested in the amount of pressure transmitted. Okay, so I'm just going to show you a very short snippet of hydraulic pressure. It's just going to be a few seconds. Okay, you will see that there's a ball that will be shown later, and that water is being pumped into the ball. When the ball is fully filled with water and you keep pumping, the water will spill up equally in all holes on the ball. Okay, this is a demonstration of Pascal's principle. All right, so let's move on. So how do we identify a hydraulic question from a liquid pressure question? Okay, a very simple way to identify that the question is a hydraulic question is simply that the liquid in the question is completely enclosed. And the second one is there's a presence of a piston where the pressure is applied and transmitted. All right, so it's a very simple telltale sign that this is a hydraulic question. All right, so similarly for liquid pressure, usually the easiest way to identify that it's not a liquid pressure question, it's not a hydraulic question, is that there is no pistons to apply the pressure. Okay, so let's do one hydraulic question now. Now imagine if I have enclosed liquid. See, the liquid is enclosed here. The liquid cannot go anywhere, and you apply a force of 20 Newton on the left piston, which has an area of 1 mm square. Okay, what is the force F that will be experienced on the right piston, which has an area of 5 mm square? The second question is, if this left piston goes down by 50 mm during the pushing process, how much does this one goes up, the right piston? Okay, so I would like you to pause the video now and try to solve these two questions, and then once you're done, you can restart the video. Okay, so have you solved the question already? So let's go to the first part. Okay, let's solve the first part, which is to find the force F. So the pressure on the left pistons will be equal to F over A, which is 20 Newton divided by 1 mm square. So you have a pressure of 20 Newton per mm square. So this pressure is transmitted equally throughout, so the right piston will have the same pressure as the left piston. So the right piston will also have a pressure of 20 mm square on it. So since we know that the right piston is also governed by the formula of F over A, so F divided by A for the right piston will give you 20 Newton per millimeter square. But as we know that the right piston has an area that is 5 mm square, so if you do your math, you will realize that F becomes 100 Newton. Okay, you're bringing the A over, and A is 5, so 5 times 20 will give you 100 Newton. So in short, the force on the right side is actually 5 times bigger than the force exerted on the left side. Alright, that's why hydraulic can be used to apply a small pressure to lift a very heavy load, because hydraulic helps to multiply the force. Okay, so let's go to the second part, which is much harder. How do you find the distance moved on the right piston? Okay, to answer that, you must first know that the concept behind it is called conservation of the volume. Alright, the volume is conserved when you push the piston down on the left side. Okay, a volume of water is being displaced on the left side. This volume of liquid, I better use the word liquid. This volume of liquid on the left side that has been displaced cannot disappear. It has to go somewhere else. So the only place it will go to is the right piston, because only the left and right piston can move. So that means that the volume decrease on the left piston will be equal to the volume increase in the right piston. Okay, and then you have to also take note that it does not mean that if the right piston will rise by the same length as much as the left piston falls. That means that the left piston falls by 50 mm. It doesn't mean that the right piston will increase by 50 mm. Alright? It is not the length that is conserved, but the volume. Okay, I'm going to explain a little bit more. Okay, look at this diagram again. So what I'm trying to say just now is that if this thing goes down by 50 mm, it does not mean that this thing will go up by 50 mm. Alright, this is just the change of length, but actually what happened is there's a change in volume. There's an exchange in volume. So how do you visualize this? This is actually, you can imagine this as a cylindrical vessel. Like for example, you can imagine this part to be a beaker with an area of 1 mm square. So let's say you have a liquid that is 50 mm in height, alright, in this beaker with a area of 1 mm square. So let's say you want to transfer this liquid to another vessel which is representing the right piston, since the right pistons have an area of 5 mm square. So this vessel here have an area of 5 mm square. So if you pour this liquid from here to here, alright, would you expect that this second vessel, the liquid, when it goes into this second vessel, will have the same height? Or do you expect it to be lesser? Alright, intuitively you will say that it will be lesser, because now the area is bigger, so the liquid will have to spread out over a larger area. So obviously the height will decrease. So the idea of how much this goes down and how much this goes up is the same idea as pouring a liquid from a smaller vessel to a bigger vessel. Alright, so using the math, first of all, you know that the volume decrease on the left is equal to the volume increase on the right. So since the volume on the left is given by 50, the depth that it decreased multiplied by the area 1 mm square gives you 50 mm cube. So the volume increase on the right will also be 50 mm cube. So because of that, we can also equate the volume of the right to this 50 mm cube. The volume on the right can be expressed as the distance increased by the liquid on the right piston multiplied by the area of the right piston equal to 50. So with this information, we can conclude that the distance moved is 10 10 mm. All right. So that's how you solve for the conservation of volume. So let's move on to the next part of the lesson, which is on atmospheric pressure and how can we understand atmospheric pressure. All right, to understand atmospheric pressure, we just have to understand the idea of liquid pressure first. Okay, let's say you are a person standing at the base of a pool of water that is 20 meters deep. All right. So the pressure that the water exerts on you will be equal to H rho G, which gives you 20 meters times 1000 times 10. All right, which will give you 200,000 Pascal. So imagine if you try to swim up, all right, there will be less depth of water on you as you swim up, and your pressure will decrease, right? Until you reach the surface where your pressure will become zero. So in a similar way, atmospheric pressure has the same idea. Okay, so the pressure on the person is equal to the depth of the air from outer space to the person. You can consider that the outer space is vacuum. There's no air, so there's no air, there's also no pressure. So you can consider that the air has a surface, and this is so-called the surface, the boundary between outer space and air. All right. So what happened is that this is only a hypothetical value. Later I'll explain why. So imagine there's 8,200 meters of air from the surface of the air to you, all right, which you are standing at the sea level. So what happened is that this depth of air is acting on you. And given that the density of air is 1.22 kg per meter cube, if you do your math, H rho G, you'll get 100,000 Pascal, which is the typical atmospheric pressure on Earth. So in the same way, if you rise up, okay, in altitude, as you climb higher, your pressure will decrease because your H decreases. Okay, so yeah, just to summarize, therefore the higher we go in altitude, the lower the pressure as the depth of air above us is reduced. But then if you look at this analogy, it doesn't seem to be the full picture, because air cannot be so short, because the highest mountain is even higher than 8,200 meters. So what's the reason? Okay, in reality, the atmospheric extends much further than 8,200 meters. As we know, that Mount Everest is already 8,848 meters. So what's the reason? Okay, the reason is because pressure reduces much faster the higher you go, as the gravitational field strength as well as the density also decrease. As you remember, the formula is equal to H rho G. H decreases, rho decreases, G decreases. So the reduction in atmospheric pressure is much faster. So because we need to have the same pressure acting on us, the atmosphere is actually stretched much further and much thinner, causing the atmosphere to be much higher than 8,200 meters. Okay, so you must remember, at least you will know that gravitational field strength is reduced as we go up, as we learn it from the topic of mass, weight, density. Okay, the higher we go, the gravity pull is lesser. Okay, so this is the idea of atmospheric pressure, a very simple analogy. So yeah, so that's the end of for this lesson. In the last part, I'll be talking about the manometer and the barometer, as well as the conversion of mmHg. All right, so stay tuned for the last lesson. So thank you and have a nice day.